Hi, good morning. Today we are going to discuss about population sampling distribution, etc. So let's start with the concept of population. So the formal definition, the aggregates under study is called the population. So the items about which we are conducting our statistical study is known as a population. So if you are studying about the income distribution uh, of the peoples in or employees in Kerala, then that's our population. Or if you are studying about the mileage of tires used in, say, passenger cars, then that's our population. But in practical sense, the collecting data from all the points in a population is not an easy task. So usually we collect data from a portion or a subsection of the population, and that is known as a sample. Then, uh, so in order to study about the mileage of tires used in, say, passenger cars, we can collect a sample of size, say, 50, which is collected from passenger cars used in, uh, say, Kerala. So uh, we can choose those 15 number of tires among all the tires used in Kerala. So we can have different combination or with different samples. We can have different samples of size 50, which can be chosen from the same population. So if all those samples have the same probability of being chosen, then that kind of a sample is known as a random sample. So a random sample of size n is a sample chosen in such a way that uh, each possible group of size n from the population has the same chance of being selected. So that is known as a random sample. So in statistical study of a particular population, we usually depends on random samples. Then if we calculate a quantity from the sample, then it is known as a stat. So usually we calculate the parameters like the arithmetic mean obtained from the sample, which is usually sigma xi divided by n, which is the arithmetic mean, and this is a static. Or if you calculate the standard deviation of the sample points obtained, then that's also a static. In this chapter, we are dealing with the static x bar and the proportion of a particular property among in a present in a sample. So if we are uh, collecting data from among, say, students, and from the sample we check whether a particular student have a weight greater than 70 or not. If it is greater than 70, then uh, greater than 70, then when we call it as a success, and otherwise we uh, so if you have a sample of size n, and if we count the number of persons with weight greater than 70, then it we can have less, or let x be the number of persons with weight greater than 70 and n be the sample size, then we can have the ratio between success and the total sample size, and this is denoted by p bar, and it's the proportion of success in a sample. Then this is a static which is obtained from a sample of size n. Then uh, we already mentioned that we can have different samples from the same population of size n. And for different samples, we can have different values for the static. For example, if we calculate x bar from a particular sample, then x bar has a value, say, um, a particular value. And when we have another sample of size n from the same population, the value of x bar may vary. So, for example, if we collect 10 students from uh, the population and find their average weight, then it can be something like 60.73. And if we if we take another 10 students and calculate their average weight, that can be something like 65.23. So this is possible. So the value of X bar vary from samples to sample, and we can have a number of samples from the same population with the same size, say n, and X bar varies from samples to sample, and the sample is taken randomly. So this X bar is a random variable, and if X bar is a random variable, then X bar have a probability density function, and that probability density function or probability distribution is known as the sampling distribution. So X bar has a sampling distribution, P bar has another sampling distribution. So that is what we are going to discuss in our next sessions. So if you calculate the sample mean, then the first thing which can observe is aspiration of x bar is equal to mu and variance of x bar is equal to sigma square by n. So what we have is if we have a population which has a mean mu and standard deviation sigma or variance sigma square, then if we collect a sample from a sample of size from this particular population and calculate its arithmetic mean, then the arithmetic mean is a random variable, and we can find the mean of this arithmetic mean or acceleration of x bar, and that is happens to be sigma. And if we calculate the variance of x bar, it is equal to sigma square by n, or the standard deviation of x bar is sigma by root of n. So that is the first thing which we uh, have about the static sample mean. Then regarding the sampling distribution of the mean, if x1, x2, etc., xn are samples of size are sample of size n from a population with mean mu and variance sigma square, and if the sample size is large, that is a size which is greater than or equal to 30, then X bar will have approximately a normal distribution with mean mu and variance sigma square by n. And if the population has a normal distribution, then X bar will be exactly normal distribution with mean mu and variance sigma square by n, independent of the sample size. So if you have a normal distribution, then the arithmetic mean will follow a normal distribution with mean mu and variance sigma square by n. And if you have a population with any distribution, uh, and if we have a large enough sample collected from the population, then the sample mean will follow a normal distribution with mean mu and variance sigma square by n. That's an approximation, but when n is greater than 30, we have a large enough sample, then this will work. And if the sample size is small, and if the population is known to be a normal population, then we can use normal distribution for the sample mean. And if not, if the population is not a normal one, and if we have only a small sample, then normal distribution is not applicable. Then, if you have a population and we are looking for a particular property, like we already mentioned, if we take a person and check whether his weight is, say, uh, less than 80 or not, then if we count such persons and measure the proportion between persons with less than 80 and the total population, that is a proportion of this particular property. And that kind of population is known as a binomial uh, population. And if we collect a sample of size n from a binomial population and calculate the proportion p bar or p hat from the sample, that is known as the sample proportion. So we collect a sample of size n and count the number of persons with weight less than 80 and calculate the ratio x by n. X is the number of persons with weight less than 80 or which has the required property. Then this p bar is also a random variable and uh, is sampling distribution. Sampling distribution of p bar is again for large samples. P bar will follow a normal distribution with parameters with the mean p and variance p into 1 minus p divided by n. So it's the mean of the normal distribution p, and variance is p into 1 minus p divided by n. And the sample is said to be a large enough sample if n into p is greater than 10 and n into 1 minus p is greater than uh, 10. So that's the condition in which we can consider the sample is a large sample. Anyhow, uh, in this particular situation, just remember one thing: if you have a normal random variable, uh, say x is a normal random variable with the mean mu and standard deviation sigma, then x minus mu by sigma is a standard normal random variable. So this result is applicable to the sampling distributions also. So if x bar is a normal distributed random variable with the mean mu and variance sigma squared by n or the standard deviation sigma by root of n, then this is also a standard normal random variable. And p bar is given as a normal random variable with the mean p and variance p into 1 minus p divided by n. So the standard deviation root of p into 1 minus p by n. Then if we consider this ratio, this will be also a standard normal random variable. So the sampling distributions of x bar and p bar in large samples can be approximated as normal random variables, and if we use the appropriate transformations, then we can convert it into standard normal random variables, and which will help us to find probabilities related to these statistics. Then uh, estimate is something, say if you have a population, then usually a population has population distribution has some parameters. Say for a population, normally if it is a normal population, we have two parameters, mu and sigma or sigma square. Then uh, any value suggested from a sample which can be used as a um, value of the population parameter is known as an estimate. So instead of the mean, we can suggest the arithmetic mean, the geometric mean, or the median, mode, etc., as an estimate of the population parameter mu. But uh, the population parameter mu. But there is a desirable property which is known as unbiased estimate. Uh, if M is a estimate of the parameter and M is obtained from a sample and M is a statistics and for it has a sampling distribution, and if you find the expected value of M and that will coincide with the population parameter, then this kind of an estimate is known as unbiased estimate. Then for the population parameters like mu and sigma square, the unbiased estimates are the arithmetic mean for mean, uh, that is defined as sigma 1 by n sigma xi. And for the variance of the population, an unbiased estimate is given by 1 by n minus 1 into sigma xi minus x bar the whole square. Xi minus x bar the whole square. So these two estimates are unbiased estimates, and usually the standard deviation calculated using this particular formula is denoted by S bar square for variance, or Sx square. We use this first notation uh, in our further discussions. So these are the unbiased estimates of mean and variance for a population. And we have the probability density function of this particular unbiased estimate of mean. The probability density function of the standard deviation or variance can also be calculated or identified, but that's not part of our syllabus and we are not going into that. But anyway, the based on this probability density function of or the sampling distribution of x bar and p bar, we can have uh, a confidence interval for the estimate, and that is our next discussion. A confidence interval for an unknown population parameter is an interval that is predicted to contain the population parameter with a certain probability called the confidence level. So, for simple example, if you are looking to find the value of the population parameter, the population mean, and we give a interval AB uh, which contain the parameter or which with a confidence level of say 90% confidence, we can say that the value of mu belongs to the interval AB. That's the concept of confidence interval. We have a confidence level with which we can assure that the population parameter belongs to this particular interval. And this interval is calculated based on uh, a sample. Uh, the process is we calculate or we take a random sample from the population, and based on the data obtained from the random sample or the calculated value of the statics, usually x bar for mean, x bar, we obtain an interval like AB, for which we can have a predefined level of confidence to assure that the population parameter belongs to the particular interval. So that's the concept of confidence interval. And this is the confidence interval for the population mean. If you have a population uh, and a sample collected from the population, if the population is is normal distribution, then any sample will work. And if it is not a normal population, we need a large sample. Then, if we have a sample collected with a size n, then we calculate the arithmetic mean of the sample. Then we can have uh, the confidence interval as x bar minus z alpha by 2 into sigma by root n, where sigma is the population standard deviation and n is the size of the sample. X bar minus z alpha by 2 into sigma by root n, x bar plus z alpha by 2 into sigma by root n, where z alpha by 2, z alpha by 2 is the value of the standard normal random variable in such a way that if this is our standard normal curve, then the value of z alpha by 2 is a value of z in such a way that this two tail ends will contain uh, a probability of alpha. Here it have alpha by 2 and here also we have alpha by 2. In total, these two tail ends together contain a probability of alpha, and this area in between minus z alpha by 2 and plus z alpha by 2, we have an area of 1 minus alpha. So that kind of a value of Z is denoted by Z alpha by 2. Anyway, this is our confidence level 1 minus alpha. Then this interval x bar minus Z alpha by 2 into sigma by root n, x bar plus Z alpha by 2 into sigma by root n is the 1 minus alpha into 100% confidence interval for the population mean. It is 1 minus alpha into 100% confidence interval. Usually we talk about 99% confidence interval or 95% confidence interval or some case 90% confidence interval. So in that case, alpha is equal to 1% or 5% or 10%. That's the value of alpha. In percentage, but usually we take the value of alpha in um, probability, that is it is 0.01 in probability or 0.05 in probability or 0.1 in probability. So here alpha by 2 is 0.005 or 0.025 or 0.05, and we can find the value of alpha uh, Z alpha by 2. You can find the value of Z alpha by 2 for all these usual uh, confidence levels. Okay, anyway, if the value of sigma is unknown for a large sample, we can always replace the sigma value with the sample standard deviation, which is calculated using the formula um, S bar is equal to sigma xi minus x bar the whole square divided by n minus 1. Remember, that is the formula for standard deviation, which is an unbiased estimate. So uh, this unbiased estimate of the population standard deviation, this is not the standard deviation actually. Uh, This is the expression for a square. And this population variance can be an unbiased estimate. And uh, is square root is the standard deviation, and the standard deviation, population standard deviation, can be replaced with if the population standard deviation is unknown, then we can replace it with the sample standard deviation, provided the sample size is large. And these are the values of Z alpha by 2 for some uh, commonly taken confidence intervals. So 95% confidence interval, the value of alpha by 2 is 0.025, and the corresponding Z alpha by 2 value is 1.96. And so what does mean? If we are looking for a 95% confidence interval, and we calculate the value of x bar, and we have the value of sigma, then the confidence interval is x bar minus 1.96 into sigma by root of n, comma, x bar plus 1.96 into sigma by root of n. This will be the 95% confidence interval. So if you're looking for a 99% confidence interval, this value of 1.96 is replaced with 2.58. So that is how we obtain confidence intervals for the population mean. So with the 95% confidence, we can say that the population mean belongs to this particular interval, x bar minus 1.96 into sigma by root n, x bar plus 1.96 into sigma by root n. You can have these values from your N01 tables uh, or from your calculators. So there is no need to remember these values like 1.96 or 1.65, but in most of the cases, we are looking for 95% or 90% or 99% confidence intervals. So then for large samples, the confidence interval for uh, population proportion is given by p hat minus z alpha by 2 into s, p hat plus z alpha by 2 into s, whereas is the standard deviation, which is given by square root of p into p1 minus p divided by n, where its p bar is calculated from the population uh, and which is given by p hat is equal to number of success divided by the sample size. If we calculate this ratio from a particular sample, then the population proportion uh, belongs to this particular interval, p bar minus, say, p bar minus 1.96 into s, comma, p bar plus 1.96 into s with a 95% confidence, where this s is given by square root of p into square root of p bar into 1 minus p bar divided by n. Remember that n is also inside the square root sign. That is confidence interval for the position. So the next thing is testing of hypothesis, that will be discussed in our next session.